So good afternoon everyone. Shall I share? Okay. So let us start. So this will be the last lecture for unit number 2, where we are looking for CPU scheduling. Last time we discussed one of the scheduling algorithm, that is round robin scheduling. Important part in that was the time quantum we select. It is the amount of time for which processor is assigned to the process, and once this time is finished, scheduler will be activated and it will select the next process. Right? It is more or less, I can say, a circular queue kind of a thing, where if 3 processes are there as shown in the diagram, say for example P1, P2, P3, then P1, then P2, then P3, then P1, then P2, then P3, something like that. But if any of the process is finished because of its burst time is less, say for example P2 is finished, then P1, P3, P1, P3, taking alternate turns. Say P3 is also finished, then it will continue P1, something like that. So whatever the example you see right now on your screen is for time quantum equal to 4. Okay, that is mentioned here. Time quantum is equal to 4, and 3 processes are there. Burst time is 24, 3, respectively 43. Now P1 will be scheduled first to execute for the time quantum that is equal to 4, so 0 to 4. Now P2 will execute for next time slot, but complete slot is not required as length of time slot is 4 and burst time for P2 is 3. So between the time 4 to 7, P2 gets finished. Without wasting one time unit, scheduler will select next process, that is P3. These processes also don't utilize the complete time slot as length of slot is 4 and burst time is 3. And once P2 and P3 is finished, then after only P1 is there, so P1 continues. Okay. The example definitely shows this gives you the better response time. Like SJF gives you always less average waiting time. This algorithm always gives you quick response time. Right? And again, even we discussed this also. The time quantum we select because of the context switch overhead. Whatever the time quantum, it should be far greater than the context switch time, the overhead of context switch. And that is the reason if we denote this time quantum by Q, so this should be large as compared with the context switch time. So typically it is between, as I already mentioned, 10 to 100 milliseconds, where context switching time is less than 10 microseconds. So this is round robin. Now in this slide, if the process time is 10, and if we select different varied time quantums, say for example 12, then 6, then 1, something like this, here we'll get how many context switches will take place if process burst time is given as a 10. So 10 is given and time quantum is 12, no context switch required, process will be finished in single turn. Same thing if process time is 10, but now my time quantum is 6, somewhere here at 60% context switch will take place. Another process will, again next time it will be turn off this and this process will. So two times are required to finish it. So one context switch is required. Whereas if time quantum is very short, say for example just 1 millisecond, and process time is 10 milliseconds, so definitely we need to have 10 different time slots. That means 10 switches are required. Participants, please yourself. Okay. So that is the relation between the size of time quantum and number of context switches. Right. Next, let us see this time quantum versus average turnaround time. So there is definitely effect of this length of time quantum on turnaround time also. For example, if you see it here, the processes P1, P2, P3, P4 with CPU burst time as 6, 3, 1, and 7. As you see, if the time quantum 1, the average turnaround time say 11. Whereas if it is 7, it goes 10.5, and it is highest whenever it is. Now for this example, actually 5. Okay. Like in other algorithms, the waiting time is varying. There was no effect on turnaround time. You imagine like even first come first serve also, or shortage of first or SRTN. But with round robin, and again we are not considering here the context switching overhead. If that is also added, definitely turnaround time will be more than that. Of course, this is average turnaround time. So that is effect. So in order to select the time quantum for round robin, it is necessary to see what kind of processes are there in our system. And one statement mentioned is 80% of CPU burst should be shorter than Q. So whatever the time quantum, say for example here 6317 we selected. So 80% of this should be shorter than Q. Okay. So for example, maybe select 6 or 7, definitely the average turnaround time will be less for this. I think this is the last one, because the priority scheduling will finish. Then again, two versions I can say, preemptive and non-preemptive. So we started our journey of algorithms, scheduling algorithms, especially CPU scheduling algorithms with first come first serve, then SJF, then preemptive version of SJF SRTN, okay, then the priority based, then round robin. Now this is multi-level queue, okay. Now in modern operating system, applications are not categorized in any single category, right? We have variety of applications executing simultaneously, and then we need to treat those applications as far as scheduling is concerned, depending upon its nature. Okay, and for that purpose, usually whatever the ready processes, or rather I can say the processes which are waiting in the ready queue, it can be partitioned in two queues. One is foreground and one is background. Foreground, they are interactive applications, and background, they are running. Say, for example, suppose you are interacting with browser. So browser is your process, and maybe you are surfing some websites, and in next step, think of that as a separate process. You are downloading something, right? So whenever you are downloading something, you are actually not interacting with it. So that download is in progress in the background, right? Whereas wherever you are actually interacting, maybe you are providing some sort of input, output, you are handing to events, then those are all foreground interactive processes are there. So given these two, maybe we need to handle the scheduling separately for separate partition of processes or separate category of processes. Okay. Background processes are like batch processes also come under this. So in multi-level queue, we create a separate queue, not necessarily now just two, maybe multiple also. Depends how many different categories you wish to have for your different processes. So separate queues are created, and then we can apply the scheduling within the queue and between the queue also. Okay, and separate items for separate queues. So for example, if foreground processes are there, then definitely we need better response time. We'll go with round robin, whereas if background processes are there, they can be treated with first come, first served basis. So multi-level queue is not altogether separate scheduling algorithm. It is like utilizing existing for separate classes. And we need to do scheduling maybe between the queues now. Now for a specific queue, that is fine. We utilize any one of the algorithm depending upon the nature of the process. Whereas between the queue also we can deal with some separate algorithms. So for example, we can have fixed priority scheduling. Meaning of this is, so all from foreground, then from background, that will possibly result in starvation with fixed priority scheduling. See, one of the policy, we already discussed this part, starvation. Starvation is like due to high priority or due to one of the parameter that is selected for scheduling process. Many few processes, one process are not getting chance of execution. That typically happens in case of preemptive algorithms, wherein imagine something like priority based scheduling. So a process with priority 5 is available and process with priority 9 is available. Okay, so which one will be selected? If there are two processes in the ready queue with priority value 5 and priority value 9, now which process will be selected? 5, correct? Because last time I mentioned the value of priority, lesser the value, higher is the priority. Now definitely the process with priority 5 is selected, and before finishing 5 one more process arrives there with priority 6, that will be selected. Before finishing that one more process arrives with priority 3, that will be selected, and a process with priority 9 is just waiting. So this situation is called as a starvation, and one of the solution we mentioned for that is aging, where as process passes more time in the waiting queue, not waiting queue, ready queue, okay, per some time unit will increase the priority of the process. Increasing priority is like decreasing some number out of that, and definitely that aging policy will give chance to that process. Now this is not fixed priority, right? We are changing the priority of that process at runtime. Whereas whatever solution mentioned here is about fixed priority. For example, if there are two queues, one is foreground and one is background, first upon will provide service to all foreground and then background. Okay, so this is one of the solution. Second thing is time slice. So now if multiple queues are there, maybe it will happen like I'll select first upon first queue, then next queue, the next queue. Now within the queue, yes, already scheduling algorithm is there. Now we are talking about between the queue. Okay, so even it is possible to divide the time. For example, 80% of the time for foreground and 20% of the time for background, something like that. So multiple solutions are possible with multi-level queue scheduling. This gives you, for example, there are 5 queues. The highest priority queue hold all the system processes, and lowest one may be like student processes. And then the order is at the top, highest priority will be system processes, then for interactive processes, then interactive editing processes. Like for example, users are typing some sort of programming assignments, or they are building their resumes, something like where they are actually making use of keyboard and interacting with them. You may again wonder why this interactive is having higher priority than editing, because whenever it comes to editing, definitely the speed of the keyboard, I can say, the user accessing keyboard is very less as compared to uh, other interactive processes. Okay, below interactive, maybe we have some sort of batch processing. So in all, for example, there are 5 queues. So this is Q1, this is Q2, so on and so forth, and this is Q number 5. Okay. Now how to schedule it? How to schedule it? Now, as I mentioned, 2 ways. One is within the queue and one is the between the queue. Now, for system processes, what I'll do is open one quick polling, and what I'll do is, let me delete this. For system processes, we know that we have FCFS algorithm, then we have SJF, then SRTM, then priority. I'm just mentioning the names of algorithms. Then we have round robin, and just open me. For system processes, which of this algorithm is good? So last 15 seconds. Just see the poll results. So 36% student given the correct answer priority, because the system processes are there. They are basically served making use of priority based. So that is the correct one. First come, first serve, no is not utilized for that. Okay. So next category is for interactive processes. Just respond here. For interactive processes, which of the following algorithm is useful? Of course. I'll respond quickly. Last 10 seconds. See the result. Now the problem, because 32% of the students saying HCFS, which is actually wrong. Correct answer for this is round robin. For interactive processes, round robin is the best suitable algorithm. Okay. Even interactive editing process also, it should be round robin. Whenever there is an interactive thing, always remember round robin is suitable algorithm for that. Now, for batch processing, yes, respond quickly. Last 10 seconds. See the result. This is for batch processing. So now look at this. Why we need multi-level queue scheduling? Because in operating systems, think of something like your desktop operating system where we have all types of processes. There are few system processes, few interactive, there are few batch processes are there. Okay. Even in case of student processes, last, if they are interactive, we'll go with RR. If they are not interactive, maybe we'll go with HFS, something like that. Now the next question is, now for system processes, yes, we may go with priority. Here we may go with RR. Here also we may go with RR. Batch processing, maybe or something like that. The thing is, between queue, what we want to do. Now, maybe we'll do something like this. This end will be connected somewhere here. This end will be connected somewhere here. And that creates a single queue. So at last, it will be something like this. Getting it, no? So this is what the fixed priority scheduling between, but definitely this will result in some sort of a starvation. So student process may get very few chance, very less chance for execution, as there are interactive processes, batch processes, system processes, something like that. Okay. Now, one of the statements mentioned in the previous slide was, which I skipped, is whether the process belong to the same queue or they can change the queue. That means one process is there waiting since long. Then maybe that process is shifted from this queue to this queue, from this queue to this queue, so that there are more chances of acquiring the CPU for execution. That switching from one queue to next, rather I can say upper queue, upper in the sense priority, is like implementing aging policy. This could be the solution for the starvation. Okay, so this is multi-level queue scheduling. A process can move between various queues. Aging can be implemented this way. That is what I just mentioned. Okay, multi-level feedback. Now one more thing is added there. Multi-level feedback queue scheduler. We can have multiple parameters, how many queues we want to have in the system, what are the scheduling algorithms for each queue, so this is within the queue, what are the methods used to upgrade a process when it is spending some X amount of time in particular queue, what are the methods to determine when to demote, like we are upshifting the process, you should be able to demote also, downgrade also. Okay, and we need to think of a method that can be used to determine which queue a process will enter when that process needs service. Like for example, even though we mentioned student processes, can it be system process? No. Can it be interactive? Maybe, may not be, something like that. So these are general guidelines we need to think of while designing the scheduler with multi-level feedback queue. So separate CPU scheduling algorithm, but in order to deal with variety of processes in the system, it is possible to categorize those processes in few number of categories. That denotes the number of queues. Say for example, in this slide, what we saw is 5 queues are there, and then we can select a separate algorithm to select the process from the queue, and maybe separate scheduling algorithm to select the queue itself. Out of 5, which one select? Or maybe like for example, in previous, what we can do is we'll switch between the queue making use of round robin, and within we have a separate algorithms. Or even it is also possible, like I give 3 turns to this, 2 turn to this, 2 turn to this, 1 turn to this, and 1 to this. Okay. So total how many? 1, 2, 6, and 9. Total 9. So definitely a process here will get chance after 9 scheduler activations. Okay. So it is not any of the style. So this is multi-level feedback queue. For example, this is the example for multi-level feedback queue with 3 queues are there, where Q0, you think of this as Q0, this as Q1, and this as Q2. Okay, and how it works is, maybe we use round robin here with time quantum equal to 8, round robin here with time quantum equal to 16, and HCFS here, where one end of the queue is connected to the next. So something like this. Okay. So 3 queues. Algorithms, each queue could be different with some different parameters. And now how scheduling happens is mentioned here. Whenever a new job enters Q0, which is so CFS, no, this one, within this queue. When it gains CPU, job receives 8 milliseconds. If it does not finish in 8, job is moved to Q1. So job from this queue will be moved to next queue. Now at Q1, job is again, so don't get confused with this HCFS and I mentioned round robin here. Now this round robin is for between the queues, right? So in this queue, for example, multiple processes are there. So here P1, P2, P3 is there. Then out of P1, P2, P3, which one will be selected? That decides by HCFS. So at Q1, again, so using and receives additional 16 milliseconds. And it still does not complete, again it will be downgraded to Q2, where it will be like it will be printed and switched to queue number 2. So this is like any combination of existing algorithms can be utilized under this multi-level feedback scheduling. I think that is all about CPU scheduling. Only one thing is still important, that is the thread scheduling. Now regarding thread scheduling, let me share one whiteboard. Fine. Now the process scheduling and thread scheduling. In operating system supports thread scheduling. Now depending upon which threading model is used, only thing is processes will not be considered for scheduling, rather than threads will be considered for the scheduling purpose. You may wonder then, for example, if there is no thread in my program, what will happen? Answer to that is operating system creates one implicit thread, and I think that is what happens in Java programming language also. So even though you don't create any thread, by default with every process, and that is typically called as a single threaded processes. So you don't need to create a separate thread. Implicitly operating system creates a thread. Okay. So what happens in that case is, if you start your program, by default one thread like that, and that will be considered for scheduling purpose. Okay, so that is thread scheduling. Important part I want to talk about this scheduling is multi-core or multi-processor. Both are one and same for scheduling, and how to draw the Gantt chart for that. So for example, suppose this is the timeline, okay, and maybe we have this as, let me select separate color. Suppose this is timeline of core 1, this is core 0, processor 1, something like that. Okay. And now suppose we have processors, something like P1, P2, P3, and P4. Okay. And maybe the CPU burst required is something like, let me select 6, 5, 7, 4, something like this. So P1 needs 6 units, P2 needs 5, P3 needs 7, and P4 4. Now, in earlier algorithms, now imagine any. Now, for simplicity, suppose first come, first serve. Okay. So if there is only one core and P1, P2, P3, and P4 arrived in the order P1, P2, P3, P4, now P1 will be executing for 0 to 6. So what I'll do is, suppose my time 0 is somewhere here. Now, if there is only one processor, what happens is, P1 will be for 0 to 6. Maybe somewhere here. Then next to 11, then 11 to 18, next 7 minutes, and at last 18 to 22, something like this. Assuming single processor. So 0 is here, then we have a 6, then 11, 18, 22. So during this time, P1 will be executing, P2, P3, and P4. Now, because we have two cores, what will happen? This will not change, right? Fine. So what happens here? At time 0, definitely we can start with P1 also and P2 also. So assume this time unit is something like 5, then maybe this one is something like 6. Actually, it should be, this should be 6, And on another core, maybe somewhere here it is 5. So now two processors will be selected. P1 is taken by first processor, for example, so it will execute from 0 to 6. 0 to 5, processor 2 will execute. Second process, that is P2. Now because it is first come first serve, this processor first of all becomes free. So from 5 to 12, P3 will be executed because this is freed first, and 6 to somewhere here 10 because P4 need 4 unit times. Okay, so somewhere here 10. So core 0 executes P1 and P4, core 1 executes P2 and P3. Now you need to compare this with single core. In single core, the overall time we required was 22 units. Here, so you imagine that as a turnaround time, right? Here, see, at time unit 12, everything is finished. That is one thing. Next thing is, if you the waiting time. In earlier example, waiting time for P1 was 0, for P2 it was 6, for P3 it was 11, and for P4 it was 18. So 6 plus 11 plus 18 divided by 4. That was the average waiting time. But here with multiple processors, P1's waiting time is 0, P2's waiting time is 0, P3's waiting time is just 5, and P4's waiting time is 6. So it is just 6 plus 5, 11. Whereas previously it was 6 plus 11 plus 18. This is called as scheduling with multiple cores or multi-processor scheduling. That was just last point I want to add it here. Because multiple processors are that we can start executing multiple processes parallelly, right? I already given the difference between the concurrency and parallelism, right? So it is how it works. I think that is end of this unit. Do you have any doubts? Have you gone through the interactive part I mentioned there? Of course, that is not related to scheduling. But what I say is go through it on the Moodle. Any doubts? If you have any doubt, you please put your questions in chat box. Because we have still 10 more minutes, so we can discuss. Nine participants are there. Maybe from next lecture we'll start with unit number 3, and side by side we have to carry out two components of ISE. Okay.